So we have kind of seen two computation interpretations of linear logic before by cut reduction. One is we had a little functional language, a little lambda calculus, and there was some proof reduction there, which gave rise to some computation. And we also had the concurrent interpretation by the pi calculus, where we had communication as being the proof reduction. So what does it look like on proof nets? Okay. So if you remember proof nets, the relevant part is that we have two kinds of nodes. We have a tensor node, and this would be labeled A, B, and so then this part down here would be A tensor B. And we can have a coupling that cuts with the dual formula, which is a negated formula. And so the negated formula would be a par, which had an A perp up here and a B perp up here. And then a cut link would connect these two. And it's okay because this is labeled with A perp par B perp. And this is labeled with A par B, and the two are opposites, so we can apply cut to the two. Okay. So can anybody guess what the cut reduction would be, what this would reduce to? Yeah, you have it. Right. So we're now cutting not A par B with A perp, but par B perp, but we're cutting A with A perp and B with B perp. So the one cut, okay, decomposes into two cuts. Okay. Now this is the cut reduction. Okay. This is very similar to what we did when we cut, right? Tensor on the right, tensor on the left. We took one cut and we decomposed it into two cuts, right, of the two premises. We actually had to make a small choice whether we cut A first or B first, okay, in the tensor left, tensor right rules. Here, this difference is eradicated because of the graphical notation. The two inference rules commute, but they give rise to the same proof net, so there will be you will be able to distinguish which one is done first, okay. It's also clear that in this kind of picture, if you're in the purely multiplicative fragment, the proof net is getting smaller as part of this reduction, right, because you just remove these two nodes here. So the number of connectives in the proof net actually goes down, even though you get more cuts, but you have fewer connectives. Now there's actually two other cut reductions we have to worry about. What would those be? So what else do we have in proof nets? It's purely multiplicative, so we have tensor and par. What else do we have in our proof nets? Cut links, and the other one is axiom links, right? Connecting the axioms, which correspond to uses of the identity rule at the top of our sequence proof. Okay. So we could have a cut of some A or some A perp, where this is connected by an axiom rule to some A, right, like this. Okay. Any idea how we're going to reduce this?
Just get rid of the cut.
Yeah, so we get rid of the cut. And so what does the picture look like over there?
Whatever is connecting to the A on the right just connects directly to the A on the left.
Yeah, so we take this terminal up here and this terminal down here, and we kind of connect those. So it essentially becomes just a straight line. So this thing up here is this one, and wherever this is connected, it's down this here. Okay. Okay, so actually the cut and the axiom both go away. And that also mirrors what we had in our sequence formulus cut elimination. If we have a cut with the identity rule, the cut disappeared and we just picked one of the premises. So the cut and the identity both go away because they're kind of opposites of each other. And you can kind of see this even graphically, right? The cut connects them this way, and the axiom connects them this way. So they're opposites, A perp, and we get that. Okay. Now there's one other way we can get the same kind of picture, namely if the cut is on the other side. Okay, if there's another axiom link here, but the outcome will be the same. Okay. So also something gets smaller in this step because the cut goes away and an axiom link goes away. And in fact, this formula, A perp, goes away. And these two, from these two occurrences of A, we just get this one link. Okay. So with that sort of graphical proof, you can immediately see that cut reduction, cut elimination is strongly normalizing. Okay. You can pick any cut, okay, and you can perform the reductions any order you like, because the proof net gets smaller at every step. Okay. Perhaps that's not so surprising because our logic is so degenerate. We don't have replication, we don't have persistent assumptions, we don't have additives, so there's not that much that can happen. It's also confluent in the sense that no matter which order you carry these things out, you always get the same answer. Okay. Because the only possibility for more than one rule applying, where the rule is kind of, would be things which are sort of different cuts that don't connect to each other, or a cut rule with an axiom on the left and an axiom on the right. And if you look at that case, you see in each case you just reduce it to a straight line. And so the two ways of reducing the cut actually turn out to be the same. Okay, so cut reduction is very easy to see is strongly normalizing and confluent on proof nets. Okay. The other thing you can see is that if you remember our proof of admissibility of cut, we had these essential cases where we had like a left rule for connective meeting a right rule for the same connective, in which case we reduced it to cuts on smaller formulas. And that's just something like this, right? So we had tensor left and tensor right. Here you have tensor and par, but it's the same picture. We reduce cut on a compound formula to cuts on the components. Okay. Now, we had other kinds of rules in cut elimination. Anybody remember what those are?
We had to like move the cut up past.
Right. We had to move the cut up past other inference rules, right? Because if the formula that we were cutting was the last one that was a left rule applied on one side and the right rule on the other, then we can do the essential reduction. But if some other inferences was applied, then we had to move the cut up in order to get into a situation where the right rule meets the left rule. Okay, and then we could reduce it. So we had to move it up past the other rules. That's called commutative cases using commutative conversions. Okay. So it's similar to what you did in the homework exercise where you check which inference rules can commute. And here we're saying that we can commute the cut upwards in the proof. Okay. Now it turns out here there are no such cases. Okay. So we don't need any commuting conversions. Okay. So the three important properties are here that it's strongly normalizing, it's confluent, okay, and there's no commuting conversions. And the reason there's no commuting conversions is because the proofs that would differ by the commuting conversions develop into the same proof net, so you can't actually distinguish what they are, right? So there might be some other rules that are applied otherwise in the net, but eventually the tensor rule is going to be applied here, and eventually the par rule is going to be applied here. And what happens in the rest of the net, which is the rest of the sequence, doesn't really affect this particular cut, and you don't need to push it up. So it has very nice, pleasing properties, okay? So proof nets are actually very nice in that way. The basic problem is it doesn't generalize very easily, okay, to other types of, to richer logics, right? And people have worked on this for a long time, but sort of more than 20 years after the introduction of proof nets, we still don't have a good formalism for proof nets that handles units like 1, okay? Which is the next possible next sort of natural generalization beyond this would be to add 1, okay? And the problem seems to be that there's not enough structure to have a simple geometric criteria for whether the proof net is valid. Okay, and so Beniamino, who was here last week, has done some work on this for the intuitionistic case, and also where you can recover some of the structure where you can have proof nets that include units. But I'm not going to talk about it in these lectures. Just wanted to let you know that they exist. Okay, so anybody remember the criteria for when proof nets are, no, when nets are actually represent proofs?
about every switching.
Yes, every switching. Okay, what the switching is that for every par node, you pick one of the two edges that are coming in. Okay, and for every switching, so globally for the whole net, you consider every par node and you pick one of them. Okay, so you get 2 to the n switches, where n is the number of par nodes in your net. And for every such switching, what do you have to check? It's acyclic and it's connected. Okay. Okay. So it's a valid proof. It's a valid proof net if for every switching, the result is connected and acyclic. Okay. So if you want to integrate mix into the proof nets, and I gave you some motivation last time for doing that because it corresponds somewhat to concurrent computation more closely, then you just drop the connectedness criteria. Okay. Because the mix rule, which is this, in classical linear logic, if you look at it from the point of view proof net, it says you have a proof net for this, you have a proof net for that. You just construct one for this by just putting them next to each other. Okay. So the only thing that you're losing is you're losing connectedness. Okay. So it's fairly easy to integrate, and these results about cut and no commuting conversions and so on, they continue to hold if you have the mix rule. Okay. So proof nets that model mix are just like the ordinary proof nets, except they don't have to be connected. Okay. And also, yeah. And you have the case of 0, right? The empty proof net, which is not valid, normally would be valid if you have mix 0, right? Because from the empty, you can prove the zero error version of that is this, right? Which corresponds to an empty proof net, which is now valid. Okay. So mix is fairly easy to model, okay, in this kind of a setting. Okay. So the other thing I wanted to mention is that we talked about what happens in the translation from the classic to the linear case when we use the parametricity of the double negation translation using p equals 1 to show that if you have the mix rule, it corresponds to simply computing, not to find a contradiction, but simply to use up all your resources, which is a fairly good model for concurrent computation of a closed set of processes. Okay. And so this is the kind of thing that allows you to put together 2 independently computing sets of processes and have the conglomerate compute, okay, which seems like the natural thing to do. And so then the question is, well, how would we do that in our original setting where we were working in the intuitionistic linear logic, right? So is it possible to take 2 sets of processes and put them together into one so that they can independently compute? Okay, so what would that be? Well, in our translation, we would have gamma, and we have delta 1 prove some process P, which does this. Okay. So this expresses as we may be using some resources, okay, but we're not actually offering some service to the outside. Okay. And then we have another one, Q, okay, which also does the same thing. And so if you combine these two and we just join the resources, okay, we should be able to compute P and Q in parallel. Okay. So how do we do that? How do we combine these two? Any ideas?
You can prove that from one tensor 1 you get 1, right?
Yeah.
So you sort of compose that with listening in those 2 channels.
Okay.
Create another process that produces 1.
Okay, you can do that. The problem is when you combine one tensor 1, that's inherently, remember A tensor B, we had to assign some kind of a sequential interpretation. What that says is you compute A, you output a channel Y of type A, and you continue as B. So there's an inherent asymmetry in that, right? So it would be a left to right composition if we did it that way. We would do P first and then Q. So we need to find a slightly different solution. Even though in the end it might end up being similar, I'm not sure. Okay, we could cut them directly if we had a 1 here, right? Okay, so let's try that. So So what is the proof term associated with the one left rule? Anybody remember?
You send a empty message.
Okay, so because it's in the context, it's actually receiving. If you do it the one right, it's ascending. Okay, so we receive an empty message, and then we continue with Q. Okay, so now if you apply the cut, then we get gamma, delta 1, delta 2 together. We have a new x. We have P in parallel with x input Q. Okay. Right, so we haven't achieved our goal, right? Because it's still sequential, because the way we cut it this way, we're saying do P first, when P finishes. Okay, that's what this is waiting for, then do Q, right? Now I could add the one left here and then do cut the other way. You see that? So instead of adding the one left here, the situation is entirely symmetric. So I can apply the one left here and then cut it the other way. And that would do Q first and then P, right? In either case, it's a sequential composition of P and Q, right? Okay. So that's kind of unfortunate. So the question is, how can we recover the parallel composition of P and Q? Yeah?
Can we have another process which is not P and Q, but it will wait 2 signals coming from X?
Say it again?
So I create another process waiting for 2 ones on some channel, say Y, and then we can direct both X and W to Y.
Possibly.
I think you still have to wait for one to terminate and then the other.
Yeah, but the order is not.
Okay. I'm not sure if it's possible, but it's a good idea. I never thought of this. Okay. But it's potentially worth looking at just to make sure, just to see if it works or it doesn't. So we pursued a different solution. So our solution is to say, well, when we build this term here, x input y dot q, there's actually no strong reason why q would have to wait for this to finish. Okay, so we can make a different process assignment, which is x input, and when you see it terminate, and put that in parallel with q. And that's okay because this x is really not in scope. Q doesn't depend on x. Okay, so we give a different process assignment than this one, where it's rather than being a prefix, okay, it's done in parallel. Okay, so we're still waiting in some sense. Some process here is waiting for x to terminate to clean up the communication with x, but we can evolve with q. And then here what happens is that you have x input 0 and then q in parallel. Okay. So it introduces a little bit of asynchronicity into the calculus. Okay, so the one rules are not synchronous the way they were before. They now have some slight asynchronous flavor because of this. But it means that we can essentially compose P and Q, and they can now independently work. And so this will wait for P to finish, and there's some other process, if we cut this with something else, that waits for Q to finish, but they can work independently. So maybe your idea would also work. We could maybe also do that. I'm not completely sure. Okay. Okay. Okay, does that make sense? Okay, so let's move on. Okay, talk a little bit about implicit computational complexity. Okay. All right. So the general idea behind implicit computational complexity is to have some kind of a type system that you assign to a lambda calculus, like a functional language, so that the only programs that are well typed are those that satisfies some time or space bound. Like just by the fact that it's well typed, you would say, okay, it's going to have to be polynomial time, or it's elementary time, okay, or it's polynomial space, okay. So in other words, rather than having some kind of external reasoning component where you try to reason about the complexity of your function, you set it up so the only functions you can write in a well-typed way are those that that type well. Now it turns out that in order to do that, linearity or affine logic are kind of a crucial thing. Because if you don't have the logic that's affine, at least, where assumptions can be used at most ones, you can duplicate things, and it's very difficult in a type system to get the duplication under control, and therefore the complexity of the functions. Okay. So I'll have a couple of examples that show the kind of things, the kind of phenomena that we have to control. Okay. So I should probably say that there is many approaches, and there's many different logics. So there is, I think, originated this particular line of research using linearity with Girard, something called light linear logic. Okay. Then there is soft linear logic, bounded elementary logic. So there's a whole zoo of different restrictions of linear logic that can be used to control the computational complexity of the function that you can write. And one thing we'll see in today's lecture, that one of the problems is, so what you get in these kind of typing systems, you definitely get a bijection in the following sense. If you can type a function in this language, then it ends up being, let's concentrate on the poly time case. It'll be in polynomial time, and you can take any polynomial time function, you can express it in this language. Okay, so that's very nice. Okay. Now the big problem is in this whole line of research is that you can express every function, but you cannot express every algorithm. Okay. So in other words, there might be a very simple algorithm, let's say, for multiplying two numbers. Okay. And certainly multiplying two numbers are not exponential as polynomial time, and therefore we should be able to write it down. But as far as I know, nobody's ever actually written down a multiplication algorithm, okay, in any of these functional languages, because the way you would have to write it down is very counter to the way that you normally think of multiplication as being defined on numbers. The natural definition will not be well typed. Okay. So there is this problem, this gap between extensionality and intentionality. Extensionally, any polynomial time function, we know we can actually compute. And the way that's done is by we simulate a Turing machine that does it. Okay. But who writes Turing machines? Yeah. And even worse, who simulates Turing machines, right? So we'd have to simulate a Turing machine that somebody else writes. So it's a very, actually with ordered linear logic, we can do it. So, well, anyway. So it's actually interesting. I don't know that anybody's actually really written down like multiplication in these kind of formalisms. Okay. And the thing is kind of, it's even worse in the early approaches, because in the early approaches, there are no data types. Okay. So instead, we go to second-order linear logic, and then we encode data types by so-called church numerals. Okay, so you don't even have like successors. Okay, so it's mostly sort of foundational interest that you can really do that. Okay, sort of mathematical interest. Nevertheless, so I tried to find something that is reasonably practical. Okay, so we can go through it, we can write some programs, and we can see if it makes sense. And so the paper that I picked is one by Martin Hoffmann on linear types and non-size increasing polynomials. It first appeared in '99, and then the journal version in 2003. Okay, so let's go. But you should realize there's dozens and dozens of papers with different proposals for doing that. But as far as I can tell, the story is pretty much the same in all of them. They're nice from a theoretical point of view, but you probably don't want to program in them. Okay. Because, maybe the first 3 programs that you write are fine, but the 4th program that you think of is not well typed. And then, the theoretician will come, oh, but I know I can implement it. But how? Well, I don't know. Let's write a Turing machine. Okay, so. Okay. All right, so remember the way we did natural. We do have to do things. Well, we don't have to, but in this paper, it's good to work with numbers in binary notation. Because if you have numbers in unary notation, the size of the representation is equal to the size of the number. So a lot of complexity considerations go out the window to start with, right? Because you want to work with binary numbers when you actually think about complexity. So we're going back to this representation where n is defined as epsilon, which corresponds to the number 0. Then we have no digits at all. And then we have n followed by 0 and n followed by 1. So this is 2n and this is 2n plus 1. Okay, so we write the least significant digit there on the right. Okay. All right, so the first function I want to define is something like, this turns out to be a useful thing, which is bracket x. Okay, so this is sort of an approximation of x where all the digits are 0 except the one at the top. Okay, so somehow we want it to be 2 to the size of x. Okay, so let's quickly define size of epsilon. It should be 0, and size of n with anything there is size of n plus 1. Okay, so that it's the way you expect. It's a number of digits in the binary representation for the size. So this takes the size and takes the power of 2 of that, so it's roughly the same length, maybe off 1 digit. Okay. So how do we define that? So in order to know that, we have to think, how do we define functions on numbers in this representation? Well, the simplest way to do it is by iteration. In iteration, there are 3 cases, right? One for this, one for this, one for this, and we can make a recursive call on the components each time. Okay. So this is a schema of iteration. Okay, so we would say f of, if f is supposed to compute this number here, okay, what would f of epsilon be?
1.
F of epsilon would be 1. F of n 0. So how do we do that? How do we do f of n 0?
Twice f of n.
Right. It's twice f of n, and twice f of n is just by taking f of n and then appending 0 at the end, right? And the function f of n followed by 1, it's also f of n, except we add 0 at the end, right? So all the digits are just converted to 0, and when we're at the end, we just have a 1 there. Does it make sense? Okay, so for example, if we take f of 7, the 7 would be epsilon 1, 1, 1. By this iteration there, we would get this epsilon would turn into a 1, which is epsilon 1, and then we'd have 3 zeros, right? So if you want to be precise, this 1 here could be written as epsilon 1, right? Okay, so we just turn all the digits into zeros and we have the 1 at the top. Does it make sense? Are we okay here? All right. So this is a schema of iteration. So we have to give it some constant expression here, okay, for the case that we're at 0. Then if you have a digit 0, we have to get something that involves the recursive call. And for digit 1, we also have to give something that involves a recursive call. Okay. Okay, so the next function we want to write, so this is f of n equals bracket n. Okay, so next thing is we want to write bracket n squared. So we want to have something that's not linear, but actually quadratic. Okay, so how do we do that? So it's sort of multiplication by itself. It's not full multiplication. And I already mentioned full multiplication turns out to be hard to define. But how to define n squared? So let's call g of n is supposed to be bracket n squared. Any idea how to do that?
The first one,
You have an idea?
For epsilon, it has to be epsilon, because 0 squared is...
For epsilon, it has to be 1, because 1 squared is 1.
Oh, bracket.
Okay, so that part's easy. So how do we do this in general? How do you square a number if it's a power of 2? You double the number of zeros. So how do we represent that iteratively? Yeah. Instead of leaving 1 0 behind, we leave 2 behind, right? So we have exactly twice as many digits. Okay. So that's the same thing as squaring the number, multiplying it by itself. Okay. So that's the size of n squared. Okay. So I put this function down because it's interesting, because it's something that actually increases the size. So it turns out that in the kind of system, this kind of function turns out to be problematic in the system that he's talking about. Okay, so why is that? Well, let's define another function. Okay, so now I'm going to look up to make sure I do the right thing. Okay. Okay, so this function I probably can't remember. So h of epsilon is 2, and you know how to represent that. H of n0 equals this function g applied to h of n, and h of n followed by 1 equals g applied to g applied to h of n. Okay, right, that's the function. Okay, so the claim is that this function h, it actually is exponential. H of n equals 2 to the bracket of n is the claim. Okay. So if we have a system that controls so that all the functions that we can write in the system are polynomial, then somehow this function h has to be disallowed, right? Otherwise we would be failing. We should probably check that, okay, whether this is the case. So we do some kind of inductive proof, right? So if n here is 0, then we're in this case. So it should be 2 because it's 2 to the 1. So we're okay there. Okay, so now let's calculate. If we have h of n followed by 0, which is 2n. So what happens in that case? So then we call g of h of n. And so inductively, that should be g of 2 to the bracket of n. Okay, what is that? What is g? Is supposed to be the bracket of 2 to the bracket of n squared, right? Okay, so if we have a power of 2 and we take a bracket, that should be the same, right? So we should get 2 to the bracket n squared, and that should be 2 to the 2 bracket of n, and that's 2 to the bracket 2n, which is what we needed to show for this to be the case. Okay. Okay, so what's happening is that if you compose these two functions, and they both look very linear, okay, still we can get exponential behavior. Yeah?
We will double the number when it is over.
Hmm?
For example, 0 becomes 1.
Yeah.
And 1 will become 2.
Yeah. That's why we have 2 here. Yeah.
I mean, it's not. I think it's not legal to get rid of the bracket in the sort of step.
It's like 2 to the brackets of n plus 1, right?
Yeah, something like that.
Okay. Where? So here?
In that step,
Yeah.
you get rid of the outer brackets. I don't think they're actually equal.
Yeah, it's 2 to the bracket plus 1.
Where's the plus 1 coming
Because like brackets is f, right? So epsilon goes to 1.
Okay, so either I'm making a mistake here in the calculation or
I think we just defined f wrong.
we defined f wrong.
Well, it gets one longer.
Right, like do we actually want it to have the same number of digits? Like 2 to the side of it have the same number of digits as that?
That's hard to achieve, right? So I thought I checked this, so let me see. What is h of, let's see, epsilon 1, right? What is that? So it's g of h of epsilon 1. And what is h, what is
G of h of epsilon.
g of h of epsilon? G of h of epsilon should be g of 2, which is epsilon 1, 0, which is 2.
No, sorry, it's g of epsilon 1, 0.
Oh, g of epsilon 1, 0.
So that's going to be epsilon 1 followed by 4 zeros.
Which is 8, right? G is the thing over there. 4 zeros, right? 16. So did we get a number? Did we get a factor wrong here? So 2 to the bracket of this should be 2, right? Okay, yeah, we got some factor wrong somewhere. Okay, let me not try to fix it. But anyway, it should be clear that it's exponential because it gets only bigger if we add 1 here. Okay. Okay. So it's not equal that, but okay. All right. Okay. So because this thing is not linear, so a lot of the systems that were previously proposed for dealing with with the implicit computational complexity, they made a restriction here that you cannot recurse by calling a recursive function on the result of what you return. Okay, so if you're computing h, okay, so you cannot go in and call some other function of recurse on the result of the computation. Okay, and so that's a very rather severe restriction. Okay, so one of the examples that I get is something like insertion sort. Right. So you need to insert something so you can, you want to be able to call some kind of insert function on the result of sorting the result. Okay, so in order to do insertion sort, you sort the list and then you insert the first element into it. And so you do insert of the result of sorting something. So this kind of pattern occurs a lot. And so there's a lot of functions that you'd like to write that you cannot write when you have this kind of thing. Okay. But in these systems, this kind of thing was ruled out. Okay. So the first problem, if you want to think of it this way, is that we're calling a function on the result of a recursion. Okay. And even though this function is certainly polynomial, and there's very little going on in this function, everything seems linear and very nice, still, when you compose them in this way, then the result is not polynomial. Okay. So the other example, okay, of something that's not polynomial, okay. Okay. So it's this one. So that's another function, h prime of epsilon, okay, equals lambda y followed by 0, and h prime of x. And actually, we don't care what the digit is, so let me just abbreviate. Is lambda y h applied to x, and the result applied to h applied to x applied to y. So I put more parentheses than I really need to.
And those are H primes, right?
H primes, yeah. These are recursive calls. Okay. So here we have an iteration which actually returns a function. Okay. And so now the claim, and this could be wrong again, h of x, y equals 2 to the bracket x times y. Okay. Okay. So, okay, let me not try to bother trying to prove that. Okay. You can check it offline if you like. Okay. The problem here seems to be that this argument x here is being used twice in the recursive call. It's used here, and it's used again over here. Okay. So the problem here is the lack of linearity. Okay, in the use of x. Okay. So this kind of thing, I don't think it can arise when you have purely first order equations, but when you make it second order, so you can return the functions, then you can pass this thing another function, and so then things can explode in size. So because h is called twice here with the same x, the thing sort of explodes exponentially. Okay. So now the idea is to control this problem here. So this problem here, control through linearity. And this problem here, control by size. Okay. So what we're going to arrange is that any functions you can write in this calculus are not size increasing. So the problem here is not that you call g on that, but the analysis that the problem is that h of n returns a result which is much bigger than what you start with, which is squared in the size. So if you can arrange that the function n, before we're allowed to call it this way, does not increase the size, okay, then this kind of thing will not destroy the polynomial time property. Okay. Oh, sorry, yeah, it's g that is the problem. G is size increasing, so we're not actually going to allow that function the way it's written over there, okay, because it increases the size. Okay. So what you actually get out of that, you get a calculus where all functions are polynomial time and they don't increase the size of the input. Okay. So for example, any property that can be recognized by a Turing machine in polynomial time would have this kind of property, okay, because it just outputs one bit, so it doesn't need a bigger output. It just needs to output true or false, right? Okay, and then there is some separate consideration that you can make on how to recover the full space of polynomial type functions if you want. Okay, so that's why in this paper the title is non-size increasing polynomial time functions. Okay, but then the sorting algorithm can be written in this language because the result of because the sorting function itself will not increase the size of its input. Okay, it will return something of the same length as the what it came in with, and so sorting can be written here. Okay, so now we have to think about what this language actually looks like. Okay. Okay. So it's actually very, very simple if you already, from what we already know. So at the level of types, which are propositions, okay, we have some basic propositions like data types, which I'll define in a second. And then we have A1, arrow A2. And actually, if you just want to control the size of things and how often things are used, we don't have to use them. So these are affine function arrows, okay? Okay, and then we have A1 tensor A2. We have A1 with A2. And I think we could have unit even though I don't think they bothered. Okay, and one important observation about this is that we don't really have bang. Okay, in this language. Okay, and then the data types you kind of define families of things. So you can, for example, the natural numbers, the Booleans, and then lists where the elements are taken from some other types. And you can make up other things if you like over here. Okay. So you already know the term construct for these things, okay, because there's nothing very special about this. So we have a lambda application for this. We have a pairing and a let for decomposing a multiplicative pair. And we have pairs in first and second for this one. Okay. So one important observation about this is that in affine logic, it should be the case that from A tensor B, we can prove affine A with B. I believe that's the right direction. Okay, so let's see. So the function would be lambda x colon A tensor B. Let y tensor z equals x in. And then we have to make a pair. And we'll just put y in the first component and z in the second. Okay. So this is okay because we have to use in the linear case, we have to use both y and z in both parts of the pair. Right? And so this would not be well typed in the linear setting because we only use y here and only use z here. But we're in the affine setting, so it's okay not to use z on this side and not to use x on the y on that side. So if you have a tensor, we can make a pair out of this. So the restriction for the pair is that you can only use one of the pieces. And this basically is more general. It says you can use both parts. Okay. So that's going to be important for some of the types later on, that when we have a pair, we can only take one of the pieces out and not both of them. If you could take both pieces out, then we would violate the linearity in a bad way. But sometimes we need to have both pieces simultaneously in order to make progress. Okay. All right. So let's see. Okay, so we need to define sizes. The size function. Okay. So we want to define this for values. Okay. And so the way I think about the size is how many heap cells do you need to represent these things. Okay. So the size for a natural number is just going to be essentially the length of x. Okay. So we'll just count the number of dots that we have, okay, or the number of digits that are in the representation. And then the size at times A tensor B of a pair U tensor V would be the sum of the two sizes. Okay, I'm wondering now whether maybe there should be a +1 there, but I'm... Okay, now for a pair it's a little bit interesting. Okay, so how do we define the size for an additive pair? So an additive pair, it's unlike this. So for this one, if you decompose it, we get to use both pieces, and therefore we have to add the sizes in the representation. Here we get to use one or the other, but we don't know when we make the pair which ones we get to use. So we have to take the maximum of the sizes. Of the two pieces, okay? And then the interesting thing is for the functions. Okay, okay, so let me write this down and let's see if we can make sense of it. The reason we have to write this down is we want to be careful that our functions are not size increasing, and so we need to find what we mean by size. So it's the minimum over the set of C's such that for all U, which are values that have type A, the size of f of U is bounded by C plus the size A of U. Okay, and if no such C exists, it's undefined. Okay, so the simplest case is that if a function does not increase the size, that means the size of the output of the function is uniformly below the size of the input of the function. Okay, so a non-size increasing function is one where the constant C is 0. Okay, so the size of function f equals 0 means f is non-increasing. Okay, and then if you allow constants here, you can increase it to some extent, right? Or like by 1. So a function that allocates one new thing, one new heap cell, okay, would have C equals 1. Does that make sense, what we're doing here? Okay. So functions are classified essentially by some bound on what they are allowed to allocate, how many heap cells they're allowed to allocate. Okay. If you say 0, then it doesn't increase the size. Okay. Okay. So, okay, so now we come to iteration. Okay. Okay. So, the schema of iteration, okay, is a schema in the examples that I have. We still have one over there. So there, you want to be able to give a function by giving 3 cases for it. One for epsilon, one for 2n, and one for 2n plus 1. Okay. So iteration looks like this. Iteration over a natural number with some type A. Okay, so what we want is we want to give it the epsilon case, which is going to be of type A. We want to give it this, okay. So this is a function that takes the result of the recursive call, okay, and gives you the result of the function. So we can try to take that function, a simple function over there, and translate it. And then the third thing we need to give it if it was 2n plus 1. And again, we need to take the result of a recursive call. And then from all of that, we generate a function which takes a natural number as input and gives you an output A. Okay? So this is just essentially forming the schema as a simple function that we can apply. Yeah?
Those can be affine, right? The two.
Oh, yeah. So, right. So actually in the paper they say it's affine, but they always write this arrow. So everything is, these are like little affine things. Okay, and for the rest of this lecture, everything's affine, even though I probably will forget to write it. Yeah, thanks for pointing that out. Yeah, everything's affine. But actually, there's a restriction here. And the restriction is that the schema of recursion itself here, these things must be closed. So you can say, well, this function is closed, and this one, and this one. Or you could put the bang on the outside saying that everything underneath must be closed. Okay. So iteration cannot have any free variables, okay? And that's essentially one of the reasons why in this kind of an iteration here, rather than introducing a free variable, okay, we abstract the y on the right-hand side and keep that over here. So we return a function. So in other words, if you wanted to have a free variable, let's just instead make it into a function, okay? If you had a free variable, then you have a problem, because if you have a free variable in an iteration, these cases here, like for example when you have x followed by something, will be used many times as there are digits. Okay, and so if you had a free variable, that free variable would be used many times. So in order to type iteration, you must make sure that there are no free variables in the body of each of the cases. Actually, now that I think of it, it's not completely obvious why this would be for epsilon, but okay. I suspect something really will go wrong if you try to break that, even though the epsilon case will only be used exactly once, but okay. All right, so the bracket function that we had at the beginning, let's try to write that. So we have it over numbers, it returns a number. Okay, so how would we write that? Okay, so for epsilon, we have to return. Okay, so we have to return 1, so that would be bang, and then the thing of type n, which we put here, would be epsilon 1, right? Like this. Okay. What would be the function here? So this would be the result of the recursive call, and we have to add a 0 to that. Okay, so it would be lambda r dot 0, right? Makes sense? And then the last one would be lambda r, and we also use r dot 0. Okay. So we take all of that, and this would have type from nat into nat. Okay. So that would be n arrow n. Okay. So this thing. So this would be the affine function. Okay. So of course it's not very nice to write function this way. Okay. But you can take, if you have a sort of a definition by pattern matching, then you have some kind of an algorithm that can decompose into this kind of iteration. And you can also define recursion operators, but I'm not going to try to do that probably. So now the problem is, if this is your iteration operator, okay, that you can actually write these functions that we just wrote before. Okay, and in fact, they will be size increasing. So we lost track of that, right? Everything is linear. There's no bang in the language even, right? So the language is extremely linear. But still, with this iteration operator, we can write functions like this. Okay. No, wait, we can't write functions like this, but we can write functions like the bracket x squared and the one that uses it. Okay. So we haven't satisfied our goal. You can now write functions that are not polynomial time. Okay. And that's because you can write functions that are not size increasing. Okay, so now comes Hoffman's idea. Okay, so the idea is that you need a capability or a token in order to be able to allocate something. Okay, so we actually take the types of the constructors and we're changing them. Okay, so let's look at these. So the function. I think he calls it S sub 0. Okay, so that's the function that adds a 0 at the end, like this. Okay, so S sub 0. You have to provide a token, and then you have to provide an n, and then it gives you an n. And similarly, for the one that adds a digit 1 at the end, you have to have a token, then you give a number, and it gives you back a number. Okay, and the whole idea is that there will be no constants of this type. Okay, diamond. Okay, the only way you can get a diamond is if you have permission from somewhere in order to use one of those. Okay. So we have a new data type here, which is diamond, which has no constructors in it. Okay. So there's kind of a hidden value, which is usually just written also as diamond, but you can't write it in the source language, because if you could, then you can arbitrarily just apply these to that constant, right? And then you would lose control again over the size of things. Okay. So now let's see how we would rewrite this function. Okay. So in the iteration function now, rather than having an A and then one of these, because this one actually, you get one token here, in the case, and you get one token here. And intuitively, that's it, because when you get something, it already has a size, so there's a constructor there. Okay, so you get one token to spend in building the result from that. Okay, so this gives you one token, and this gives you one token. Okay, so then if you want to build that function again, so maybe let's do it over here. Okay, let's write it like this. So we pattern match. So we have our function, what did we call it? F? Or the very first function that just did the size. We had f of epsilon. And then we said it's epsilon 1 f of n 0. Okay, so now if you write this more formally, the pattern would be like, okay, s sub 0, then a variable c, which stands for a token. Okay, and then there would the next argument would be n or x, and then we construct S0, and we apply it to C, which we have by pattern matching here. And then the result of F applied to X. Okay? So we can construct this S of 0 because we have a token C to spend. And of course, the last case is the same. Successor 1, C, and X equals S of 0, C, and F of X. Okay. And then we can turn that into an iteration here. So what happens is that in this term here, we're going to have to write, okay, we take the result of a recursive call. But before that, we take a token, lambda C of type diamond. Then we take the result of the recursive call. And then we take S of 0, we apply it to the C and to the result of the recursive call. Okay. So that's just a new way of writing this out when we explicit that we must have permission to allocate something here. Okay. Okay.
Where do you get the cell that you need to make successor 1 of epsilon? Because f of epsilon, you need a token there.
Okay. So what's the type of f?
You're not going to need a rigor. So you just need to come up with that.
Hmm?
You just need to come up with the natural on that side.
Right. I'm just wondering where we get the token from, right?
I mean, isn't this why you don't want to have epsilon have the first argument bang? It would seem like you didn't want that. Then you could pass that into the function as a whole. That's the constant.
Right. But I'm pretty sure that's not the way that he did it. Yeah. In fact, come to think about it, this thing is size increasing, right? Because we go on one additional bit, right? So we must.
It's a constant amount of size increasing, which is
Yeah.
according to the semantics it says it.
Right. Yeah.
I'm just guessing maybe there's a decompose function that can get a number get a number appended with 0 and also the number n and recurse function.
I think if you do that, though, you'll be able to write you get more size increasing function. Should be able to come up with stuff that's going. That's the whole thing.
Yeah. Yeah. There's definitely an issue here with those constants. Okay. So maybe it goes to some later remark where he says there are certain cases which you can duplicate. Okay. So there are functions that take a closed expressions. But you can type closed constants, but I'm not exactly sure now. He doesn't talk about this, so or I overlooked it somewhere. Maybe the result type needs to be not A, but from token goes to A in order to account for the additional constructor that you need for that one. So if you do that, then there will be an additional token here that you would ignore, an additional token here that you would ignore, and a token that you take in here, and then you use that
Yeah, okay.
in this place.
And you don't ignore it, you just pass it
pass
out.
it to
Oh yeah, okay, because you need to pass it to F because you need it at the top level.
Yeah.
Okay, so then what the type of this actually would be token goes to n, right? Okay, so,
You can only increase the size by exactly 1
Right.
or 0.
yep,
write a different function that increases it by 2.
No, but this our function now exactly increased it by just 1, right?
But I mean, with that type, how could you increase it by 2?
Yes.
Oh, no, but this one you would have, token tensor token if you want to increase it by 2.
Oh, okay.
Right.
Yeah.
So token to the n if you need to increase it by some fixed amount. Yeah. Okay. So, okay, let me see what I want to do next. Okay, so then you can define a list and a case construct out of these things. But I don't want to try to do that. Now, I think the Booleans are interesting, so let me talk about that. Okay. Okay, so already at this point, the kind of thing that he claims about this language is that, first of all, all functions that you can write with this are non-size increasing, according to the definition that we have, okay? And they're polynomial time, okay? And he gives a very complicated proof of that, but there's a follow-up paper by Illich and Schrichtenberg where they give a very syntactic proof. So they actually define an evaluation strategy and show that with respect to that strategy, you have a polynomial time number of reductions. Hoffman wasn't able to get that result in his first paper. Yeah. So you will notice that also in the papers on light linear logic and so on. If you actually look at the reduction strategy that the lambda calculus would impose, it's not going to be polynomial time. Okay? And you just prove a result that if you can write the function in the calculus, then it is a polynomial time function, even though the one that you write down might not actually run in polynomial time. Okay? At least in this case, okay, it will actually run in polynomial time. Okay? Even though, like I said, in the original paper, it didn't have that result. So it could very well be that if you evaluate this with call by name, call by value, whatever you like, the thing will take more than polynomial time. Okay. But so this problem at least, or this question at least has been answered by the follow-up paper for this calculus. But for the other ones, for many other ones in linear logic, it's known that if you apply ordinary lambda calculus reduction, that you don't achieve polynomial time, even though you know that the function that you write down will be in the poly time, right? So that makes it further and further away from programming practice, right? Because you can write it down, there's no polynomial time, but it still runs exponentially. Okay, so not particularly useful. Okay. Okay, so this token trick, by the way, can also be used to control the use of space, right? And here it is controlling the use of space because you're actually prohibiting essentially allocation. Okay, you must already have the space when you start, and so I think you really need something like this in order to get this to work. Now, Booleans, there is a remark that I want to make. So the Booleans are defined with two constants, true and false, right? So we have true is a Boolean and false is a Boolean, and they have size 0 because they're constants. And then the if looks like this. Okay, it takes a Boolean, which is your condition, and then it takes two branches. So this is if with a result of type A. So this is like sort of like iteration over Booleans. Okay, and then it gives you an A as a result. Okay. So now, the way you have to combine these two here, you can probably figure this out. How do you combine these two here?
We only ever want to take one of the branches.
Yeah, you only take one of the branches depending whether it's true or false. So it has to be with. Okay. Okay. And so the typing rule you get out of this is the one that you would expect. It's this if you have delta, the derived rule, delta prime, and you're trying to prove if, and then some expression E1, and then a pair E2, E3 has type A, if in delta E1 has type bool, and in delta prime E2 has type A, and in delta prime E3 has type A. Okay. Okay, so that's how you have to define a Booleans, and this is one of the places where it's important to have this, because you cannot really determine which branch will be taken. So splitting the resources between branches doesn't really make sense. It has to be additive in this way. So that means that if you have a variable and you use it in the condition, okay, then you cannot use it in the branches. So you cannot test whether x is greater than 0 and then do something with x, because it disappears on you. Right? Okay, so that's a fairly severe problem, because you can, and so it's useful to think about which sort of elements of data types can be duplicated, or where you can test and sort of get them back. Okay, and a couple of years ago, I actually wrote some programs in this language just to see what it would be like. And you need to do this all the time. You need to take some D, okay, so some data type, probably. Okay, so a data type D is some kind of refinement of the possible spaces of all types. D stands for data type, or something that can be duplicated. Booleans can be duplicated. Okay. This can be, I'll tell you what duplicated means, and lists with element of type D, and D1 tensor D2. Okay. So what you get is this function, dup. If you have a function that takes a D to some result P, and P must have some requirements on it as well, then you can get a function which gives you P and gives you back the D that you put in. Okay. Okay.
You said diamond could be duplicated?
In this sense, right? That if you can get a result P here of a certain kind, okay, then you can get D and you can get back your diamond. Okay. Okay, it seems wrong. Because, okay, I'm going to have to check on that.
P is supposed to be like, supposed to be a base type?
Yeah, P is it's called a passive type, so I don't remember now the exact definition of what P is. But it definitely does seem wrong. Okay. Well, let me just give you. If D is a Boolean, if P is a Boolean, okay, because you couldn't have used the token in the first place, is what you're saying, right?
And if it's diamond, then that makes sense as well.
Right.
So,
Okay. So maybe this P is so restricted that you can't, if it doesn't contain lists, but just like Booleans.
I would think,
Yeah.
You can't, P should be the stuff that can't consume data.
Right. Cannot construct data.
Cannot construct data.
Yeah, right. So the case that they uses it for is for Booleans. If you have a Boolean B, let me just do it like that. Okay. So you test some condition, then you can test the condition and get the thing back. Okay. Okay, and then you modify this rule to put some other theta in here. And theta is shared between all three premises. And the requirement is that theta has things in it that are x colon d. Okay. And so now here it definitely seems to be tied to Booleans for the same reason. Okay. So you can use it here and here, and that would be the normal thing. But you can also use it in the condition, because you can use it in the condition, and you can get another function. You can get it back as a result. Okay. Okay. So this is actually like, it's been a couple of years now, so I don't remember exactly. But I remember I had to write a lot of functions that would actually take something, test some properties of it, and make sure to return the thing that you gave it. Because if you consume it as part of the testing, then you can't do anything with it, right? So that actually turns out to be an important thing. Okay, so we can relax this rule in this way, okay, in order to allow the test to involve a variable as long as the variable is of a type that can be duplicated. And the other thing he says, and this is really surprising now, okay, Another thing you can do is you can just change this rule altogether. And the way you change it is you have the same deltas here, here, and here. Okay. And if you do that, okay, then you don't get the polynomial time functions, but you get polynomial p-space functions. Okay. So you get non-size increasing polynomial. Well, you get polyspace, a characterization of polynomial space. Okay. Okay, so I don't really know how that results works because I haven't been able to go through it in enough detail to figure that really out. And it's not clear that the operation semantics that you actually run would respect the polynomial space bound on this. And I think actually, in fact, the answer is no. But he nevertheless has a proof in the paper that if you do the original rule or the rule where you can duplicate only the things which have a duplicable type, okay, where this is a Boolean here, then you get non-size increasing polynomial functions. And if you relax the requirement on this rule, then you can model all of p-space. Okay.
Is that the only rule you have to change?
Yep, that's the only rule you have to change. Okay. Okay. There has to be some good deep reason for it, but I don't know what it is. Okay. Yeah?
What I have is why this duplicable idea, why don't you just add persistence and make these kind of things persistent resources?
Well, you need to have a minimal amount of persistence here in order to make sure that these things are closed. But if you add persistence and you can package things up and you lose control over the how many times things are being used. And we saw that very simple example there where you iterate the function h twice, which was exponential. So if you add bang, you're back to having, non-polynomial time functions.
Even for these constants like, because you have to, because every time you duplicate a Boolean, you have to allocate a new. Okay, I see.
Yeah. So, yeah, I think once you add bang, then it's again a free-for-all. But it's a very interesting thing that in these other approaches, in the light linear logic and so on, there's a completely different choice being made. So there is no discussion of size increasing at all. Okay, and what we do is we remove properties of bang. So the properties of bang that we have in the general case is that bang A is equivalent to bang bang A, in that from bang A you can get A. So I guess one of these two directions is obvious. So I guess the interesting direction is that if you have bang A, you can get double bangs. Okay. And so you can just decide arbitrarily to remove some of these properties, okay, from bang. And from a modal perspective, it goes from, if you think about it as a modality, this is a modality called S4. The bang is a modality. That's the general provability modality. And you can do that kind of construction of bang for other logic. So if you do it for intuitionistic logic, you get box. And if the dual, the why not, is going to be a diamond. And then you can ask, what kind of modal property does it satisfy? Okay. And what Gerard does is he says something like, well, let's take some of these away. For example, let's take this one away. Okay. So we only have this. Okay. And then see what kind of functions we can write. Okay. And the question, we always ask this question with respect to encoding, where something like nat is defined as for all propositions P, P arrow, P arrow, P arrow, P. Okay, so we define this in the natural numbers, the data types, not by constructors and iteration, but in some kind of a higher order way. And then you have to think about where you have to put bangs in order to make these things work. And so there's some leeway in which kind of structural laws you have associated with bang, and different fragments give you different power of computation. But unfortunately, like I said, there's a problem in both directions. You can write down a function and you know it's polynomial, but you don't know how to execute it. You know a polynomial time function, you know there's an implementation, but you don't know what it really is because it's a simulation of some kind of a Turing machine. So, but if you want to abstractly know how to characterize polynomial time, there's ways to do it by using these various forms of linear logic. Okay, I'm over time. So I'm not sure exactly what I'm going to do on Wednesday, but I'll let you know. Yeah, homework's due Wednesday, last homework.